Hello, fellow nodes. I'm Corrine Wallach, Community Manager at Neo4j. Thanks for joining us for the Neo4j online meetup. Today we have a really interesting topic, how to load Bitcoin into Neo4j, and putting Mark would I say this is bold. So I think it's going to be a pretty interesting topic. I'm going to post a link to the topic thread in the community site in the chat window on the right-hand side of the YouTube video. And if you have any questions, you can ask in the chat window on the right-hand side. If you're watching after the live stream ends, you're able to actually communicate with the speaker right on this community site thread. Also, I am also going to share the blog post that is related to this topic. And unrelated to the talk, Mark, my very special colleague who is here with us today, is co-authoring a book that's going to be released very soon. It's an O'Reilly book on graph algorithms. And if you can register online and get access to a digital copy for free, if you are interested in that. And that is the link for that. So other things that probably were good, if you want to increase your visibility on the video, you can change the megapixels to 720 on the right-hand side of the screen. And yeah, you can feel free to ask questions during the talk, and we'll also have a Q&A at the end. And I'm going to let our speaker, Cesar Pantajo, take it away.
So hello, everyone. I'm very happy to be here. Thank you very much to Karine and Mark for having me. Really excited about this. So we're not only going to talk about, because the blog post on the post that we shared on the community was mostly about the engineering side on how to load efficiently the whole Bitcoin blockchain into Neo4j, but we're going to have a second part where we give a bit more details on the Without further ado, let me share my screen.
I think the internet cut out right at the last statement. If you
yeah, maybe just repeat the last thing you said, Cesar, just before you said you were going to present your slides.
Oh yeah, so I was saying that we are going to talk not only about the engineering side on how to load efficiently Bitcoin into Neo4j, but also like the kind of analytics that having the Bitcoin blockchain on Neo4j enables us to do.
That's awesome. If you guys love Cesar's talk, feel free to give it a thumbs up on YouTube.
Thanks. Okay, so yeah, that was the intro. So this is the structure of what we're going to talk about today. Of course, the introduction and the motivation. Then these are the two phases that I mentioned. First, how like the engineering and the pipeline on how to load Bitcoin into Neo4j, and then the use cases of the kind of analytics that this enables us. So before that, a little bit about our company. So we are a London recently funded company funded by Jay Prasad and Sid. We aim to be the main source of blockchain data analytics. So we enable investors, developers, and other stakeholders so they understand better what's going on. So if you check, for example, our Twitter, you can see that we're very active there, and not just commenting on the current state of not just Bitcoin, but other blockchains as well. But we also have our website where we show different data about Bitcoin and Ethereum and other various tokens. This is the team. Jay and Sid are the founders. We are a diverse team of engineers and scientists. Very talented, I must say. My colleagues are very talented. I'm very happy to be working with them. And a little bit about me. I originally got interested in graph databases, because on my PhD I did semantic web, and particularly I used another graph database, an open source database called Gina, which is specifically tailored towards the semantic web. The topic was more or less probabilistic reasoning on the semantic web. So graphs are not new for me. And when the opportunity presented to apply that knowledge into my work on blockchain, I was very happy. And in fact, I'm going to tell you why it makes a lot of sense to load Bitcoin into a graph database. So first of all, we need to. I'm going to give a little introduction for those who don't know that much about how Bitcoin works. So I know when we think on Bitcoin and the blockchain, we think of a succession of blocks, right? And that's why it's called the blockchain, because it's a chain of blocks. However, the blocks are simply holding the transactions where the actual meat of what Bitcoin is about is happening. The main unit of trading in Bitcoin are the outputs, and the transactions move and split outputs from one place to another. And I say place because here place can mean a lot of things in Bitcoin. It can be an address, or an address is basically who is locking that output, and they can be multiple outputs. And in fact, the outputs have a script, and in the script you can that script is the one that determines which addresses lock the output. But in that output, you can put in that script. You can put all sorts of clever things. It's not as sophisticated as the Ethereum scripting language, but you can still do some pretty clever things. So that's why I put place in quotes. So blocks are generated by the mining process. That's how blocks are generated. So when on the first block that was mined by Satoshi 10 years ago, he generated an output, and that was the very first output, and those were the first 50 Bitcoins on the Bitcoin chain. And since then, of course, many more outputs have been generated by the miners and so on. So to explain a bit better what this means, I'm going to give a quick example. So let's suppose that Alice has 50 Bitcoins. What this means, basically, is that there is an output, an unspent output locked by Alice, right? So that means that Alice can spend this output with a value of 50 BTC. How she got that output, it can be because someone else sent it to her, or because she mined it herself. And she wants to send this to Bob, right? So she sends a transaction which unlocks this output, and this output has. So one thing to note is that a transaction must use all the Bitcoins in an output. It's not like I'm going to send 20 Bitcoins and then this output is left with 30. It's not like that. Like, you have to use the 50 Bitcoins in this output. So this output has to be used entirely. So she's going to send 25 Bitcoins to Bob. So this transaction uses one output as input and produces two new outputs, each for 25. And the new one of the outputs is locked by Bob, and the other output is locked by Alice again. So she still has 25 Bitcoins, but it's on a separate, on another output. You can split Bitcoins, these outputs, you can split them however you like. Like, you could send the whole 50, or you can send 40 to here, or in 3 different outputs. So it's up to whoever is creating the transaction. So if we have that's what I say that's what I mean by that Bitcoin can be better understood as a graph. And I hope you agree with me that this does look like a graph. Like, you have outputs used by transactions which generate their own outputs. And in fact, I'm going to remove the addresses, and these are outputs, and the outputs are used by transactions. Transactions generate their new outputs, and new outputs, and those outputs are used by transactions, and so on and so forth. So it makes a lot of sense to treat Bitcoin as a graph. Of course, it makes also sense to use it in a tabular format, like in tables, in a regular SQL database, and we do that as well. And we do other sort of analytics with that, but the sort of power that we get with a graph database cannot be understated. So this is the schema that we have come up with. So we have the blocks. These are blocks. Blocks, like you have a succession of blocks, and we have transactions which are included in blocks. The mining rewards are generated with something called the Coinbase of a block, and it's a special type of transaction. So a transaction can be a Coinbase of a block, and then that transaction unlocks outputs and generates outputs as well. And the outputs are locked by addresses. This is something extra that we have added to our model, which is to include some extra semantic information about the addresses, because that's what we want to analyze.
Cesar, I think some of the captions aren't shown on there, but I think the yellow is addresses, right? And then the
so from left to right we have the blocks.
Yep.
Then we have the transactions, then we have the outputs, and then the addresses. And this is category and entity.
Cool.
So you can have, for example, an entity can be, for example, an exchange, BitMEX, or it can be a dark market, Silk Road, for example. And the category is, for example, if it's an exchange, if it's a dark market, if it's so we have different categories and entities on our database.
And is that the first graph model you came up with, or did you try a few, or like what was your process to come up with that model?
Because we understand Bitcoin, I think this is more or less the first iteration. So we are aware. We got a lot of inspiration from a previous effort by someone who also had an online meetup about day loading Bitcoin into Neo4j. So we did look at what he was doing. We made a few improvements, and this is the model that we came up with.
Yeah, I guess that might be the Greg Young.
I think so. Yeah, Greg was his name. Yeah.
Yeah, I just asking because often when people are figuring out how to model their data with graphs, they're quite curious how do people go about doing this. So it's good to understand how you did it.
Yeah, it does help that I pretty much have a PhD in graphs, so it did help because on my PhD I had to model all sorts of things. So I already have experience modeling graphs. So that was very useful for when it got to creating the model for Bitcoin.
Yeah, he's Dr. Graphs.
Thank you.
Not
awesome. Not quite. I hope. Yeah. So we're just gonna go and do a quick demo of a particular
Yay,
one.
We love demos.
So this is the shell. So this is a block. Let me make this bigger. I hope you're seeing correctly. So this is block, just because it's a nice number, 550,000, and it's quite recently. I think right now we are in block like 570,000 maybe. So this is relatively a relatively recent block. So we have here the attributes of the block, the hash, the number, some other data that we're not going into too much detail. If we expand this node, we're going to see the transactions. Well, some of them, because the console has a limit on the number of nodes it can show. So this is another block. Sorry, this is actually the previous block, and this is the following block. So this is block. No, well, sorry, it's the other way around. This is the previous block, so it's block 549,999. This is the block that we're seeing, and these are some of the transactions in that block. This is the next block, and if we expand the transaction, we are going to see that this transaction in particular has 4 outputs. Sorry, this is using 1 input. Let me move this a bit more this way. So this is the input, as we can see by the relationship, unlocked by, and this output has, this transaction, sorry, has these 2 outputs. And if we expand this, we are going to see the addresses that lock this and unlock this output. So this particular output, for example, we can see that was locked by this address. So this output was by this address, but this output was used by this other transaction. So this output is already spent. And there could be multiple addresses here as well. This could be locked by multiple addresses. Yeah, so let's move on. So now we're going to go into the engineering aspect of how we loaded Bitcoin into Neo4j and how we did it efficiently. So we split it into 2, and actually there was a question this morning in the forum post about the distinction between historical and ongoing. We made the distinction because historical, like Bitcoin is already in its as I said before, in its 500 and something thousand block. If we try to load that like using the normal method, that's going to take a long time. So that's why we have to use this historical load, which is a lot more efficient. And then the ongoing, we use regular Cypher queries to insert in the database. So the first step is to get the data out of the nodes. So Bitcoin, as you probably know, it's a P2P network. It's not a lot unlike the torrent network of a particular file, so of a particular torrent, where many people share a file, except that this file is the distributed ledger of all the outputs and inputs that we just discussed, of transactions as well. So if you want to get into Bitcoin, you have to, so the information is in the nodes. So we have to spin up nodes if we want to get the information out of Bitcoin, of the blockchain, right? And the main implementation of Bitcoin, of the Bitcoin client, of the Bitcoin protocol, it's called Bitcoin Core. Oops, sorry. And the client exposes JSON RPC methods, which you can use to interact with the client. So you can install this on your machine, and you can be part of the Bitcoin network. Like you're not mining. This is not mining. This is like regular nodes that validate the blocks, but they don't generate new blocks. And you can install, and you yourself, you can do JSON RPC calls to this blockchain. However, getting information from using the RPC methods, like you have the overhead of the whole HTTP stack when you want to get information about a particular block or about a particular transaction. So this particular step is not specific to Neo4j, because the information that the output of this step can be used to populate also, like whatever we want or we need. In this case, it's Neo4j. So we wrote a custom RPC client, which gets the information about blocks and about transactions and stores in a binary format in a data lake that we have. It is being housed currently in Amazon S3. And we can even query that data lake using, for example, Amazon Athena. So using various optimizations, we are able to perform this step in 3 hours. So we have several nodes and several clients connecting to those nodes and writing to the data lake. Spinning up a Bitcoin node for us is also very quick because we have the chain data, as it's called, backed up. So if we want to spin up a new Bitcoin node, we simply spin it up and use the backup that we have to initialize that node. So So that's super quick for us as well. I don't know if anyone has any question about this, the first step, or should we just move on and then later you can have any questions?
Yeah, the video is going to be a couple seconds delayed. So if
okay.
people ask questions, you could just continue asking, and then Mark's watching the chat, so he'll
Perfect.
relay the questions to you if they're relevant at the moment too. So please feel free to ask questions, viewers.
Yeah. Okay, so once we have the information in the data lake, it's time to load it into Neo4j.
Somebody did ask what the size is of the data lake.
The data lake is around, I think, 1 terabyte, about 1 terabyte, because we do use binary because this explodes. So, like, the main information is blocks and transactions, but then we also have we exploded that into blocks, transactions, inputs, outputs, addresses. So so we have all that like schema on the data lake. So it is about 1 terabyte. And if you're wondering, we have it in both formats, in two formats, in Avro and Parquet. Parquet is a columnar format, so it's easier to query. But if you want to query, you have to load the entire file. On the other hand, Avro is more better suited for like serial access, so we can access record by record. So for this case, we use the Avro files. So we from those files in the data lake, we generated CSV files, which are the ones that are going to be loaded into Neo4j. And we use, like I said before, we use the Neo4j admin import tool because this skips the transactional layer of the database. So there's no need to worry about commits. There's no need to worry about logs, indexes. The downside of this is that you have to use this in a completely new database. Otherwise, we would just use this for everything. But no, this has to be used in a new database. So that's why we went with this road. The CSV files are generated in about 3 hours, and they end up being about 300 gigabytes. But importing the CSV files into Neo4j takes about 1 hour and 10 minutes. Because the addresses, like I said, they don't really exist in Bitcoin. They are simply like the signature of a private key that logs a certain output. In fact, you cannot query the RPC, the Bitcoin node for a specific address. Like you have to query for blocks and transactions, and then the transaction will include all the inputs and outputs. That means that the list that we extract from the Bitcoin node has like a historical of all the addresses that have interacted with the blockchain, including like if an address has appears twice in the blockchain, then we will have the record twice. And the Neo4j admin import tool expects that the records are not repeated. If you can pass a flag for it to ignore repeated records, however, that we found that took longer than if we deduplicated the records ourselves. So we used the Linux like unique sort and unique command to deduplicate that CSV file. And the deduplication takes about 30 minutes. And then loading those CSV files into Neo4j, another 40 minutes. So I guess that's one tip. If you want to import and your CSV files have repeated records, we found that if you can deduplicate the records outside of the admin of the import tool, do that, because it was quicker than having the deduplication done by the import tool. The resulting Neo4j database is about 1.3 terabytes. It does include some indexes as well, so we created some indexes. So this 1.3 terabytes includes some indexes. Now moving on to the ongoing loading. So because we generate the CSV files at a certain point in time, right? So all the blocks that are generated after that, they won't be included in those CSV files. So we need to keep the database updated. And for that, we modified the RPC client to not only write to the data lake, but also to send to Kafka, which is a streaming architecture that a streaming platform that it's pretty cool. Jendrik, our Kafka expert in resident, who can probably tell you more about it. So you can hit him up about it.
He's on the live chat, so.
Great. So you can also ask questions about it. So Kafka, it's pretty cool. It allows us to, for example, if you go to our website, you can see our SDK that we have a streaming SDK. So you can get real-time information using WebSockets about transactions and about all sorts of amazing stuff on the blockchain. So that's the reason that we chose Kafka. So from Kafka, we wrote a connector that writes to Neo4j, but from Kafka, we can write connectors and consumers that can write to all sorts of places. So that's pretty cool. Okay, so now that was how to load the Bitcoin into Neo4j. Now I'm going to give you some quick examples on how, like the type of things that Neo4j enables us to do. So, for example, if you want to find the UTXOs, so yeah, UTXOs, like I said before, maybe I wasn't very explicit, but the specific term for outputs that are not used is unspent outputs, or UTXOs. That's how it's spelled. Unspent transactions, unspent outputs, sorry. So these are outputs that are circulating that can be spent. And if we run this query, we will find all the outputs that are not used currently on the whole in the whole of Bitcoin network. We are not going to run this because this is probably going to take a very long time. But you can see very easily that it's very easy it's very natural to understand once you start thinking about the blockchain, about Bitcoin in a graph. It's basically outputs that are not unlocked. And this is the Cypher query for that. So match all the outputs where they are not, where this particular edge relationship doesn't exist. That will give you the outputs, the unspent outputs. And in fact, the Bitcoin, I think this is better because the Bitcoin node, the Bitcoin nodes, the implementation, they keep a separate database of the unspent outputs. Here, we don't need a separate database. We can just check the outputs that are not used. Another example, for example, if we want to find the balance of an address, is the outputs that are not spent. So again, these are all the spent outputs locked by this address, and then we simply sum the value of all the outputs that we match. And this one is one that we can run. So in particular, this address has 0.0005 Bitcoin. I don't know how many $1,000 is that, but yeah. So now let's check another one. For example, we can find. Sorry, remember that we had an extra attributes for the entities. For example, exchanges. So Bitfinex is an exchange, and we can find, for example, the balance that Bitfinex has on their wallets, because we do know like we have some algorithms and some data sources that tell us different addresses from which entities they are. Of course, this is still not 100% accurate, which it's a work in progress, but we do know some of the addresses that belong to Bitfinex, which is an exchange. Okay, so all these addresses were actually, if I remove the optional and And if I comment this out, it's going to run for a while, but this will give us a list of addresses belonging to Bitfinex and their balance. We could, for example, return the whole balance of the addresses that we have tagged as Bitfinex. Again, this is going to take a few seconds. I don't know if there's any question in the meantime while we wait for these queries to run.
Yeah, we've got some for you. So Andre asks, so kind of started asking about duplicate addresses, but your colleague has already replied to that. So the latest question is, not all nodes have a solicit address. How do you, or not all output nodes have a solicit address. How do you handle that?
Sorry, not all nodes have a what address?
It says solicit address, although I'm not, I think, explicit address.
Okay, yeah, so.
Sorry.
Yeah, no, it's fine. So in that regard, like the Bitcoin protocol standard, if you might. So again, Bitcoin Core, it's a specific implementation of the Bitcoin protocol, but there are a few others as well. The protocol specifies a few standard type of transactions or outputs, right? So or output scripts. So you have the ones. So it's paid to public key, which is the traditional one where you pay to an address, to a public key, which is the address, and you can unlock that address, right? There's another one which is the pay to public script hash, I think it's called, and that can be locked by multiple addresses or public keys, if you might. So the client. And basically, all clients handle these specific cases. They say and they even tag them. Like if you call the RPC and get the information about a particular transaction, that's going to tell you this output is of this type, and these are the addresses that are locking this output. The script is being locked by these addresses. Sorry, but of course, in the script you can put anything. You can put whatever you want. Those outputs and types of scripts are not handled by the implementations. So in those cases, I guess you could obscure where your funds are coming or going if you do some sophisticated script. But this is for this we assume these are the standard type of scripts that are locked by that locked an output basically. So I hope that answered your question. If not, then feel free to follow up later. So these are, for example, some of these queries have returned. We have a few addresses here. Like I think, yeah, these are a few addresses by Bitfinex, and this, according to this, the balance of Bitfinex is 122,000 bitcoins, which is a lot of million of dollars. I guess it's a very big exchange. So, okay, so let's go to another type of query.
From
yes?
Alberto is, do you usually use the Neo4j browser when you're doing your querying, or how are you just doing that for demo purposes? Like, what would be your normal analytics process?
So we do use it's like a sandbox. The browser. It's like a sandbox where we can test some ideas, where we can, because so the server is being hosted in AWS. The connection might drop, the query might be very extensive, and it's unrealistic that you're going to leave the computer turned on the whole night or the whole day running a query, and it's not very reliable because you might lose the connection. So we test ideas. So this is like a playground where we test ideas. We limit the results to a few records to make sure that it's doing what it's supposed to be doing. And then we run the queries on the Cypher shell on the server using detached consoles or jobs and so on and so forth. But yeah, I could say that we do, like, it is part of our workflow to use the browser. So this one is very interesting and a bit more complex. This query will give you statistics about particular entities. And we use APOC, the APOC library. So this will return in this case, for the last 7 days. We could change this for example, for the last month or for the last 30 days. But let's leave it for the last 7 days. This returns statistics about a particular entity. In this case, it returns, for example, the inflow of that to that, and in this case, exchange, the average transaction value to that exchange, the number of transactions for that exchange on a given day, number of entities, and number of so entity receiving addresses is the exchange addresses, and this is the addresses of that are sending to that exchange. If we run this, and we're also, while that runs, you might also notice that we are using, so we using APOC library allows us to run this query in parallel. So each day is one thread in the server. We normally run this for 30 days, and this 24 means that there's going to be 24 threads running each query, running for each day, basically. So let me just very quickly show you if we like what the query is doing. So if we do this, this will return the today and all the previous days. So today and 7 days and up to 7 days ago. And this is the query. So we can see, for example, for Bitfinex, for this date, there was this many Bitcoins coming in. The average transaction value was for this many Bitcoins. This was the number of transactions, the number of entity of addresses of the exchange, and the number of addresses that are sending to or receiving from that exchange. In fact, this powers, so this is our website for those who want to know it. Some of the information on these graphs are powered by the Neo4j database. For example, Bitfinex, this is for the rolling 24 hours. It's basically the rolling 24 hours version of this same query. So we see, for example, that this particular has this much inflow into the exchange, and so on and so forth. So you can start to see like the type of analysis that Neo4j allows us, and I think that nothing gets the point better than the following query, because first I'm going to show you the SQL version of the query. So this whole gigantic query, it's like 200 lines. Still going here. This is the SQL query to get statistics about an address. So this will tell you. Sorry, no. These are statistics for the whole blockchain. It's the number of addresses, the number of transactions happening in that period of time, in the last 24 hours, and the volume being moved in the last 24 hours. So this is the SQL version. You can see it's a massive query where we have to do joins and cross joins, and this is the Cypher version of the query, of this same query. So with this query, we can get statistics about all of the Bitcoin blockchain in the last 24 hours. So let's explore it in a bit more detail. So this starts in 24 hours, so from 24 hours in the past. And we get all the transactions, all the blocks, all the transactions, all the outputs, and all the addresses in where the block was created later than the start date, so later than 24 hours ago. And then we sum all the values of the outputs this is matching the transactions that are unlocking an output. And so because, like as I said earlier, you have to use the whole bit output. And what is a common practice is that if you don't need to spend the whole Bitcoin value of the output, you send the part back to you. So it's like a change, right? So let's say, for example, you need to pay for something that on the store, something that's worth £8. You give them a £10 note, and they will give you back a £2 note, right? So that's the change, literally. So of course, if we include the change, it's going to look artificially inflated, because it might seem that we send 50 Bitcoin, when in reality we sent actually 25, right? So this is matching that change volume. Of course, you can send the output to another address controlled by you. So this is not accounted here. Again, it will be in the future, but right now it's just we only account for the change when the change is sent back to the same address that sent the output. That's why it's called real. And in fact, if you look at our website, it says we have somewhere here, for example, we have real volume and change volume. So in this case, this is the actual volume that was moved, and this is the volume that was sent back to the same address. So I guess this query should, it ran in 20 seconds. In 20, that's nothing. Because the SQL version of the query, it took a few hours to run. This one runs in Neo4j in 20 seconds. So in the past 24 hours, there have been 511,000 unique addresses. There have been 335,000 transactions, and the total volume in Bitcoins that has moved in the network is close to 800,000 Bitcoins. So this can give you a metric of how healthy is the network. Is it being, is it active? Is it not? And then hopefully we can use this type of metrics to predict or analyze how the price of Bitcoin is going to move. And I think that's all I have. So maybe we can jump into questions.
Yeah, we had another question a little bit ago, but I was waiting until you finished, which was about whether you'd thought or explored doing the similar thing with Hashgraph.
Hashgraph.
I think this is like a similar thing as Bitcoin. So let me find a question. Then I
imagine they might be talking about the Merkle trees and similar, where you have like a hierarchy of hashes.
So it says, have you looked at Hashgraph? It's graph-based. They have a mirror net that receives all the events from the network. It seems like Neo4j would be the perfect solution. But I guess we can have a look at it later on.
Yeah, definitely. I'm going to write that down.
And then I think your colleague answered this already, but I guess interesting to hear your opinion. He said, do you do any fraud investigation or analysis on this data, or is that not something you've looked at?
There's an interesting application where we have the because we have the entities, right? We have we are currently working on tagging addresses where you have, for example, an address is an exchange, like we said, or is darknet, or it was being used in a scam. So we have all these classifications of the addresses. We can tell, for example, the risk, like how far removed is an address, how far is a certain address, to another address that has transacted, that is tagged as darknet, for example, or as from a scam. So, so in a sense, that will give you a risk score of an address, and that's something we are exploring at the moment. Yeah, it's not full on risk, but another
question does it work? How fast can you get predictions? I'm not sure how many seconds back in what you said that is linked to, so maybe you do.
Predictions. Oh, you mean I imagine it's the predictions of the like how the price is going to go up or down. We're still working on our models, but we can already start seeing some interesting things. Like for example, there was a spike in price. I'm sure you saw the news in BTC in the past few days. Like we can already start seeing like the big movements, or as they call whale movements, because they're like big transactions moving from one place to the other. So there was a big whale movement, and that caused the price to start spiking. At least that's one of the theories. Thanks to our bots and our alerts, and even our streaming infrastructure, we are able to get a sense of it's still not a prediction because it's not an exact science. That's why it's called prediction. But we can already start seeing some correlations and some interesting events that might affect the price of Bitcoin.
Okay, cool. Andre asked, can you use this approach for other coins? So we've actually had a talk, I guess it was 3 weeks ago, about doing the similar thing as what you've done with XRP.
Yeah.
I'm sure someone has done something with Ethereum. I don't know whether you've seen any other ones.
No, the thing with Ethereum is that it's massive. It's a scale much more larger than Bitcoin. So the block time, so the Bitcoin standard, the protocol is made in a way that there's a new block roughly every 10 minutes, right? So every 10 minutes that all the transactions get confirmed and a new block gets created, gets mined, and you have a new block every 10 minutes, right? Bitcoin started in 2009, and we are currently at block 550,000. And Bitcoin only tracks inputs and outputs, so moving outputs from one place to the other, like we said earlier. Ethereum, on the other hand, is much more ambitious in two ways. One, the block time is, I think, 6. So every 6 seconds there is a new block. So right now Ethereum is in block, I think, like 7 billion, and it only started in 2013. So it started a few years later than Bitcoin, and it's already orders of magnitude blocks ahead than Bitcoin. I mean, it has much more blocks than Bitcoin. And in fact, the chain data in Bitcoin, the chain data is 400 gigabytes. Like if you start your own Bitcoin node, you can expect it to fill more or less 400 gigabytes of 400 gigabytes of space in your disk. Ethereum, on the other hand, it's, I think, 1 terabyte. If you have a full node, it's like 1.7 terabytes. And in fact, I'm going to pitch now a website that we built some time ago, about which is called nodestats.org, where you can see all the statistics of how many resources you can expect to need if you want to run an Ethereum node. And I'm sure Jendrik must be right now posting the link to the nodestats.org, so you can see the scale of the Ethereum blockchain. The other way that is fundamentally different from Bitcoin is that it aims to be a world computer. So the script that you can run, that you can put on the chain, on the blockchain, is much more complete. So you can do all sorts of crazy things, and all of those crazy things have to be kept on the blockchain. So if you call a piece of code in Ethereum, there's going to be a record in a block somewhere that's going to say this function was called by the script. So it's a lot more information. So it's a completely different beast, and it's something we're looking to tackle in the near future, because definitely that's something that makes a lot of sense to do. But it's whoever does that is going to get some press for that, because that's massive. I hope it's us, of course.
Someone asks Amazon Web Services or local hard drive. I guess you probably you have to have a pretty big local hard drive to get that on.
Yeah, Yeah, I guess you could. Of course, you could, but first you would need it to have it always connected to the network, and it's going to use a lot of space in your hard drive, and it's going to use like CPU and memory resources of your machine. So you won't be able to go and play your game of Fortnite while that thing is running. So. So yeah, we use AWS for that, but I mean, you could run it in any cloud provider that you choose.
One more question. Do you do a historical load every day, or do you do one-off loading?
No,
or
we do a one-off loading because again, as we said, you can only use the import tool once on a new database. Once that database is initialized, you cannot use the import tool. You can use the Cypher load CSV statement, but that's a bit like that takes more, and it will be the same as running the Cypher, the insert statements yourself. And it's also better, like for us, it's more up to date. There are always records coming into the database, and we're always updating the database, as opposed to batching it in. So we do in the end up doing batches, but they are very short batches. So a new transaction comes in, and after a few transactions come in, we insert that into the database. And Kafka has some fantastic utilities for that. Like it keeps the state on itself. It's in a redundant backend as well. So if the node goes down, you can count on it picking up from where it left. But that's preferable for us than to having to run every 1 hour or every 2 hours, because that means that our data will be a bit far outdated.
Cool.
That's great.
Okay, so
We're pretty close to the hour, so I can probably wrap up. Corinne.
Pretty good timing. Yeah, I mean, we could wrap up. If anybody is watching after the live stream is over, or you have additional questions, the community link, which I can post again in the chat, Cesar, you can talk to him directly, as he's the one who posted it.
Yeah. And don't hesitate to contact me on Twitter, email, on the blog post with smoke signals, and anything that works, just hit me up, and I'll be more than happy to help and to answer questions.
That's awesome.
And just before we finish, I want to give thanks to the team at Tokenalyst, because I think this was a team effort and they did a great job. Thank you in particular to Simon and to Jendrik, because they were very helpful as well when we were working on this project.
That's great. Yeah, this is a really cool project. It's very interesting. And Mark, do you have the link to the Kafka connector again? Maybe you can put that back in the chat.
Yeah, I think we put that a bit further up.
Yeah, it's further up. I mean, if you're interested in it, scroll up the chat.
Yeah, it's in there again now.
It should be in there. So thank you. Okay, everyone. Thank you guys so much for joining us today. So thank you so much. This is a really cool project.
Thank you very much for having me.
Please give it a thumbs up if you enjoyed it, his talk. And if you are interested in presenting your project in the future, if you write a blog post, if you've already written one, post it in the community site under the content category, the Neo4j community site. Or you could just write about your project in the projects category on the community site. That's how we'll be, that's how we find out about like people's projects, what they're doing, and what other cool things might be interesting to talk about. But this was definitely an interesting one. So thank you for sharing.
Thank you. Thank you for having me.
Okay, and we'll see you guys all next week.
Bye.
Bye.